All right. All right. Right. Before we finish this problem, did anybody finish this one up here? Where we used that second alkene, and I gave you both intermediates, and we went through the arrows, the mechanisms. Did anybody finish that? And if you finished it, do you want to share it? I'm gonna stop being democratic.
I finished it, but I don't know if I did it right.
And you just put the answers in and we can discuss it.
Okay.
I'm trying to see. Are you drawing them already or no?
No, I can't find where I can draw them. I can't find the.
So tell me this. What would the 1-2 product look? Just tell me what the 1-2 product looks like that you have, and I'll put it in.
Okay, well, it looks like the second product that you have below, but I just attached the bromine to the 2 part.
Okay, so you're saying, so where's label 2? You saying you have this like that?
Yes.
Okay, that's the right product. What about the 1-4 product? Where would that go?
I have it like that as well, but the double bond, I moved it to the left, and the bromine, I moved it to the part that already has the little wedge out.
Okay, so it should be here, right?
Yes.
Like that. Is that right?
Yes.
And the alkene.
Yes. Yes, that's what I have.
Yeah, that's right.
Okay,
so
thank you.
with this question, right? Again, it's 1-2 attack versus 1-4 attack. So bromine is either going to go here. And let me fix that arrow. It's going to go here to this carbon, or it's going to go to right. Anytime you use a conjugated ion, you add HS to it, right? If I did prevalent, so I did the reaction at 0 degrees Celsius, which product do you think is going to be predominant? Is it going to be the 1-2 or the 1-4 product?
The 1-2.
Yeah, that's the kinetic product at low temperature. And then the 1-4 product, if I warm it up past the past 0, if I warm it up to 10 or 25 or 35, then the 1-4 product is going to predominate. And we talked about that, how that happens, right? It goes through like a SN1 type mechanism. So let's do this last question right here, and then we're going to move on to cycloaddition, which is the next topic with conjugated dienes. All right. So if I have the kinetic product right here, and we read the question, both products from the reaction done at 0, warm to 40, then the product distribution changes and the kinetic product is converted into the thermodynamic product. Using the major product from the reaction done at 0, propose a mechanism for how this might occur. So what basically this is so this is the kinetic product from the second reaction that we talked about from this one. right? So it's that product. And then the other kinetic product would be here. Right, so if I took those two, basically the question is asking if I took those two and warmed them up, like how could I get them, excuse me, to interconvert back to the thermodynamic product?
You make the bromine leave, and then you have to move the double bond towards the plus charge where the bromine would be. And then once you move that double bond, then it's going to create another plus charge, and that's where the bromine will attack.
Okay, so I lose the bromine. I put that arrow in first. And then you said to go ahead and do resonance.
Yes.
Like so, right?
Right.
Let me that arrow is kind of sloppy looking. So then you want to make this carbocation. And then that's what bromine is going to attack. Is that what you're saying?
Yes.
All right. That's good. And the same thing happens here, right? The mechanism for interconversion is loss of leaving group right here. That's how you get to the allylic carbocation. And then again, if you want to do resonance first, that's fine. Just to move the plus charge to here, and then that's where bromine can attack. And so that's how you get this product, right? So if you have the kinetic product and you want to convert it, not in every case, but in the case of this reaction where you have a conjugated diene that you're reacting with HX, if you want to convert the kinetic product into the thermodynamic product, then you just warm the reaction mixture up, add a little extra energy, and that added energy allows that kinetic product to revert back to the intermediate, and then the intermediate get converted into the thermodynamic product. All right, so that's addition of HX. So the other reaction that conjugated dienes do is cycloaddition. Let me put the date 3. Man, this month is over already. Wow. So cycloaddition of conjugated dienes. All right. So there are a lot of different types of cycloadditions, but we're going to talk about the 4+2 cycloaddition. The 4 is 4 pi, and the 2 is 2 pi. So that's just talking about the easy way to think about it is that a 4 pi system has 2 double bonds or 4 pi electrons, right? It's a diene. And then this is just a simple I don't want to say alkene because you can actually use alkene and alkynes, right? So the 4 pi system is a diene. The 2 pi system can be an alkene, or it can be an alkyne, right? I don't want to box us in because I know there's a couple of examples that use triple bonds as the dienophile. All right, so the 4+2 is exactly that. You take a conjugated 4 pi system, which looks like this, right? And then you take a 2 pi system, which in most cases is going to be some type of alkene, right? And when you put them together, and I'm not showing the mechanism right now, I'm just showing the outcome, you get a 6-member cyclohexene. So 4 pi plus 2 pi, you get a cyclic alkene. All right, and this type of reaction, we call it a pericyclic reaction. We call it pericyclic because the electrons I'm just going to say a specific pattern. The electrons move in a specific pattern, and only certain atoms are involved. So let me show you how it works, and then we're going to talk about the molecular orbital aspect of it, and then we're going to work through some problems. All right, and I'll send a video for this after class just to reinforce what we're talking about. All right, so this 4 pi plus 2 pi, right? It's always going to result in the same thing, a 6-member ring, right? But so I had the diene drawn like this, right? But in reality, the diene can't, when it reacts, this conformation is called S-trans. And then the other conformation that it can exist in is like this. It's called an S-cis. If you remember from part 1, you know, trans means something opposite, right? Something, it has something to do with something being opposite. And then cis has something to do with something being on the same side. So let me show you what that means. Right, so if you look at the 2 alkenes, since it's conjugated, they're separated by this sigma bond, right? So S-trans means that both alkenes are on different sides of that sigma bond. If I were to draw it, I could also draw it like this. Not like that. So now you can actually see that the 2 alkenes are on opposite sides of the sigma bond. Right, so you can see here, here. Move this out of the way. Right, so those alkenes are opposite, but the fact that it's a sigma bond means you can rotate around it, right? It's not free rotation. It costs some energy, but you can rotate around that sigma bond to rotate one of those alkenes around. So that's what the S-cis is. You can see here, if I drew it this way, right? Both alkenes are on the same side. Right, so that's why we call that S-cis. It's the S-trans is actually favored. Right, so that's why when you do the 4 + 2, you have to heat it up, right? Because you got to supply some energy so that the diene can adopt the right conformation in order for it to react. So that's actually S-trans is actually favored. So a gallon of 1,3-butadiene, 99% of it is going to be in that S-trans conformation. All right, any questions about that? All right, and you'll see why this matters in a second when we start talking about the mechanism and the transition state. You'll see why that matters. All right. So if I'm doing a 4 + 2, I'm going to take my diene and I'm going to react it with the 2 pi system. This is 4 pi, this is 2 pi, and I call that my dieno file. Right, you know, anytime you see that little suffix file, that means something. It comes from the Greek, one of the Greek words for love, right? Philos. So see that word or that suffix, you know that this is a lover. This is a lover of something. Like electrophile is a lover of electrons. Nucleophile is a lover of nuclei. A dienophile is a lover of dienes, right? So when you react, when you do this 4 + 2 cycloaddition, which we also call the Diels-Alder reaction. Right? You're reacting basically a diene and a dienophile. All right, any questions so far? All right. So the way this works is, again, it's pericyclic. So I'm going to number these atoms, right? So you can kind of follow this along. Got 3 things that's going to happen. So the diene is going to attack your dienophile. So carbon 4 and carbon 5, you're going to end up, and I'm going to draw this here too. Right, so this is what's happening, right? So carbon 4 and 5 are going to end up with a sigma bond. All right, so you need to get a new sigma bond there. And then you're also going to get a bond, wrong pen, between 1 and 6, right? So that's also going to give you a new sigma bond. Right? And then the fact that carbon 1 already has 4 bonds, already has a full octet, right? I'm going to shift this over between 2 and 3. So here, that's when you get a, right here, a new pi bond. Right, that's why we call it pericyclic, because the electrons only move within this 6 atom array. Right, so when I draw the product of that, it looks like this. Right, it is a 6-member ring, and if I number it, 1, 2, 3, 4, 5, and 6, like so. Questions about the mechanism? All right. Any questions about the arrows? Any questions about the bond formation? Anything? All right. Right, so if you recall back when we did the orbital diagrams, I made certain to do that first, right? I did the orbital diagrams for the 4 pi system and the 2 pi system. I did that first on purpose. We're going to talk about the molecular orbital consideration. right. So somebody help me out. What's a molecular orbital again? How would you describe it?
Would it be like a theoretical,
I agree that it is
Well, in class,
theoretical. I agree with that.
You kind of just said like it's like a way to predict reactivity and like the
Yes.
wave-like, particle-like properties of the electron.
Yes. So when we talked about if we have a 4-pi system like this, are you following? So it should have 4 molecular orbitals. Is that right?
Yes.
Yeah. So we built up the, let me see if I can grab it from when we first started talking about this. If it's, oh shucks, it's on a different page. Let me grab it from a different page and see if I can cut it and bring it in. Yeah, right there, boom, perfect. My dog is going crazy. Bruh, chill out. All right, so let me see if I can paste this in here. I'm probably gonna have to move or add another page. So let's shrink that down. All right, so this is the MO diagram, right, for a 4-pi system. So for the 4+2 cycloaddition, that 4-pi system is going to react through the HOMO. Anybody remember what that term HOMO means? It's an acronym for something, right?
The highest occupied molecular orbital.
Right. So the HOMO for a 4-pi system, let me zoom in on this. You see it right here? Oh, that's a bad color. You see it right here? This is the HOMO for a 4-pi system. Are you following?
Yes.
Mm-hmm. So when I look at this 4-pi, I keep screwing up this load, right? This HOMO is going to look like this. So this is going to be shaded. That's going to be shaded. This is shaded. And that's shaded. Do y'all agree? Based on what we know about the MO diagram?
Yes.
Mm-hmm. So the 4-pi system reacts through its HOMO, and then the 2-pi system reacts through its LUMO. Let me grab that right quick from that other document. Should I grab it from the right place? Here we go. He's going to town on his paws. You would think it was some barbecue sauce on his foot or something. All right, so this is the 2-pi system right here, right? So the LUMO of the 2-pi, if I draw that out, looks like this. Everybody agree?
Yeah.
You can see on the diagram that I imported, right? The LUMO is empty. That's important. No electrons. And you can see in this diagram up here, the HOMO is not empty, right? It has electrons. So the HOMO is when species act as nucleophiles, they react through their HOMO. When they react as electrophiles, they react through their LUMO, right? So we're going to say that the 4-pi system is nucleophilic, right? Because it's giving away electrons. And then we'll say that the 2-pi system is electrophilic. All right. So now let's think about this. So how do these two things come together? All right. You got the HOMO of the diene, you got the LUMO of the dienophile, and the way they come together in the transition state is like this, right? So here's your HOMO of your diene. Here's your LUMO of your dienophile. So this is shaded, that's shaded, like so. Now, I'll buy lunch for the first person to tell me how that LUMO should be shaded.
The top one on the first one is supposed to be shaded, and the bottom one on the second one.
By first and second, you mean left and right?
Yes.
So like this?
Yes.
Okay, I respect your answer, but let's think about it. Remember we said that orbitals are equations, yes?
Yes.
And they have, and each lobe, the shaded and unshaded means that that's the sign of the lobe, right? We're not saying it's positive or negative, it's just whatever sign it is, right? So if I overlap unshaded lobe and a shaded lobe, they cancel because they got opposite signs. Are you following?
Yes.
Yeah, you can't. So in order for two lobes to overlap, so you can share electrons, they got to be the same. They got to have the same sign. So I'm
Okay,
gonna
that
leave
makes
that like that. But thank you for saying. I'm still gonna cash out you though, because I appreciate this was that makes sense.
Yes, it makes a lot of sense.
It's like if you positive one, yeah, if you add it to negative one, you're gonna get 0 because they might be the same number, but they got to cancel each other out. So, right. So the lobes have the same sign so they can properly overlap, and you can share electrons. You can't share electrons through lobes that have different signs, right? So then on the same thing happens on the other side, where you have the shaded lobe and overlapping with the shaded lobe, right? Of the HOMO, the shaded lobe of the LUMO overlapping with the shaded lobe of the HOMO, right? So again, this is the HOMO of the diene and the LUMO of the dienophile overlap. That's how this reaction happens, right? It's the HOMO of the diene overlapping with the LUMO of the dienophile. Now, last thing about this, and then we're going to actually work through a couple of examples. All right. Remember I said that up here, that this has to be S-cis, right? The diene. I'm gonna put that in here for those of you who will go back and look at this later. right? So the excuse me, the diene has to be S cis. So we come down to here, right? And let's just say for the sake of argument that the diene is not, right? That is S trans. And then you still have your LUMO here. Right? So if the diene is, write that in here. All right, so what do you think? If my diene is S trans, do you think it's going to react?
Would you say no because it'll be too far away for them to overlap?
Yes. Now you definitely just earned lunch. That's exactly right. This side can overlap. Right? That side overlap is fine. This side, left. Right? The distance for the lobes to overlap, for this lobe and this lobe to overlap is too far. Right? So you can't overlap. So this will not react. Right? It won't react to the S trans. Thank you. That's a great answer. It's too far away, and so it won't react if it's in the S trans. That's why you have to heat this up. So all the reactions that we see, you're gonna see a little delta sign over the arrow, meaning heat, right? So you heat it up in order to give it enough energy for that diene to convert to S cis and then react. All right. Any questions about anything? All right. Let's have a lot of time. Let's jump in and do a couple of problems right quick. And we'll come back to those and I'll move this up. All right. So let's do this. Let me scroll up to here. All right. So now let's work through these. We're gonna work through the forward reactions, and then we're gonna work through retrosynthesis, which will be we'll probably get to that on Wednesday. And then yeah, we'll see where we are on Wednesday, depending on how things are looking. We'll see what we do next. The next section is aromatics, but I'm not sure. We'll probably start it on Monday instead of Friday. All right. So let's take that first reaction. All right. It says predicted products of the following. Remember, this is the name, the proper name for the 4+2 cycloaddition it is actually a name reaction. It's a Diels-Alder reaction. And it's very useful, especially when you're doing like synthesis of large molecules and you need to build up cyclic backbones and cyclic molecular structures really fast. This is a great way to do it. So what do you think about the first one?
Sorry.
Go ahead.
I was just asking, would you do it like the one that we did?
Every time. All of them. It doesn't matter what's attached to the diene or what's attached to the dienophile. This reaction happens the same way every single time, right? So you're gonna put in electrons here, here, and then you shift the pi bond up. The mechanism never changes. And we can number it just for, you know, just to keep us all on the same page. So in the product, what is your core product from a 4+2? It's the same core. I don't care what's attached to the diene, what's attached to the dienophile, you're gonna get the same core. What do you get?
Is it a pi bond?
Yeah, it includes a pi bond, but the core is a 6-membered ring,
Yeah.
right? The core is going to be that 6-membered ring. That's the value of this reaction, so that you can build up these six-member cyclohexenes, and then you can imagine the more substituents you put on your diene and your dienophile, right? The more functionalized it is, then, you know, when you get to that product, you can keep using it. You can use that as a precursor to something else. All right, so 5, 6 right there. All right, let's look at the next one. What do you think? Let's number it. So that's 1, 2, 3, 4, 5, 6. Don't worry about the bromine. Don't worry about the methoxy group. Can somebody annotate that screen and put those arrows in?
I kind of don't know how. Like
Yes, you do.
I say usually it'll give me like the option down here, but I don't see it.
Oh, you don't see it. Are you
No.
using your phone?
Yeah, but I did it on my phone plenty of times.
There may be some update that, you know, everything is, once you update stuff, they change stuff and don't say what. So just tell me where you would put the first arrow.
I'll draw the arrow from 4 to 5.
Okay, I agree with that. So here, like that.
Yes.
Mm.
Then the second arrow from 6 to 1.
Mm-hmm. So that pi bond, once you attack 5, that pi bond has to break, right? Because otherwise 5 is going to have too many bonds to it, right? So we at 6 to 1. I agree with that. And then what about the last arrow?
Then 2 to 3.
Right, so you shift this pi bond to here, and it doesn't change, right? Doesn't matter what the substituents are, how much spinach is hanging off of that thing, doesn't matter, right? And this is still here. And then the bromine is still here. All right, now you do, for this particular problem, we got a couple of things that we can introduce to, right? If you have on your dienophile, if you add an electron withdrawing group, right, it actually speeds the reaction up. So that increases the rate. And let me move this down. All right. So if you put an electron withdrawing group like a halogen or a carbonyl or a nitrile, like you can think about all the different electron withdrawing functional groups. If you add any type of electron withdrawing group on your dienophile, it's going to increase the rate. That's actually, there's a list of electron withdrawing groups and the ranking of them, like how you go from which one is best, which one is worse, it's in the video that I'm going to send today. So you'll be able to see that and see what I'm talking about. But any acceptor, any electronegative atom is going to increase that rate. Now, oxygen is kind of a little bit of an anomaly because it's highly electronegative, but it's also a really good donor. So go figure. Like, so oxygen is different. But if you look on the diene, it's the opposite. You have a methoxy group right here. And so that will be considered, and we put the lone pairs in so you'll understand, or at least, right, even though you got lone pairs on bromine as well, this is not as good of a donor. And it's not even as electronegative. But so when you compare the oxygen, when you put a donor on your diene, that also increases the rate. So I'm going to abbreviate that. DON, that's donor. EWG is an electron withdrawing group. So you put a donor on the diene, that also increases the rate. Right, so that's one way to that you can kind of control the rate of the reaction is you can substitute, you can add substituents on your diene or on your dienophile, and you can change the rate. The better the donor, the more the rate is going to increase. So that's another aspect of this reaction that we know now. If you add a donor on the diene, it increases the rate. If you add an acceptor on the dienophile, then that also increases the rate, right? And there's one other part that I'm gonna slide in here because we covered this already. That bromine, would that be considered a chiral center where bromine is? Oh, no, I'll say the answer at once, no?
Would it be yes?
Yeah, it is a chiral
Yeah,
center.
because the carbons are attached to different things.
4 different substituents, right? And so in reality, when you do this reaction, you're actually going to get 2 products. You'll get this and you'll get this. Hold up. Let me move this over. Right, and you can kind of see now, hopefully, how there's so much connectivity between the topics, right? That's why you can't just like cram for the test and then just forget the information, because you can see you always see stuff again. So the same here, right? So you're going to get 2 products. What do you think the ratio is going to be? What should it be?
I want to say 50-50.
Yeah, it should be 50-50, because how do we get it to not be 50-50? We talked about that. There's 2 ways. But you're absolutely right.
Something that doesn't have a chiral center.
That's a 50-50 ratio. You're right. Who said that? Because I can't see the.
I think Joy said it first.
Okay. Yeah, I can't see the icon.
I was trying to say it was racemic, but
Racemic, yeah, same thing. You're right. That's right. That's the technical term for it. But how do we get it to not be 50-50? Just jog your memory back to when we first started talking about stereochemistry. One way
Amaria
to
said,
go ahead.
I was telling you that Amaria answered it. She said to change it to something that's achiral.
Yes and no. Right. One way to do it is to take something chiral and react it with something achiral.
Yeah, that's what I said.
Yeah.
Yeah.
You need a pre-existing chiral center, right? That's what that is. You have something that has a chiral center in it already, and you react it with something that doesn't, and then you get an unequal mixture. The other way is to use a catalyst, like a chiral catalyst. I think I talked about that with y'all too. But if you don't have either one of those, then you're going to get a racemic mixture because both of your start materials are achiral, right? So achiral plus achiral gives you a racemic mixture. All right. Any questions about that? I wanted to throw that in because again, everything is connected, right? You're always going to run into something from another section when you start a new section, always, right? Organic is like Legos. If you build the foundation, you'll see that every topic builds on the next topic. All right. Let's stop here. We'll stop here. We'll pick this up on Wednesday. All right. Any questions?
Is there a video on this topic?
Mm-hmm.
Okay.
Yeah. I'm gonna send it out after class to reinforce it. And I'll open up the quiz for it too, because what we talked about here is enough. If you were here and you watch the video that I'm sending, then you'll have plenty of information to take that quiz. All right, so we're gonna stop here and let me stop sharing and start recording.